Hello everyone, my name is Pengcheng. I'm honored to have the chance to address you on this special occasion. The topic of my paper is Low Overhead Grace Degree Coding Scam for Online Fountain Code with Limited Feedback. I'm from Harbin Institute of Technology, and this is my email. The outline of my talk as follows. The first part, I want to introduce the background of this research. The second part, I will introduce the online fountain code with limited feedback. The proposed gross degree encoding scheme are provided in the third part. And then we give the overhead analysis in the fourth part. Finally, simulation results and conclusions is given. Now I will first introduce the definition of fountain codes. Fountain codes, also called rate list codes, are a class of erasure or correction codes that can generate an infinite number of coded symbols from a limited number of original symbols through the XOR operation. There are many codes that belong to fountain codes. In 2022, Ruby proposed the first practical realization of digital fountain, named LT code. In 2026, vector codes are proposed by Shaklaki through cascading fixed-rate codes and LT codes. Later, spinal codes, analog fountain codes, and online fountain codes were proposed as new classes of fountain codes to transmit data efficiently and reliably. My paper is based on online fountain codes. Fountain codes were initially designed to transmit information without feedback. However, as it evolved, it made sense to use a small amount of feedback to enhance its performance. In 2015, online fountain codes were first proposed. The online property means that once given an instantaneous decoding state, the encoder can find the optimal coding strategy efficiently. Due to the excellent characters of online fountain codes, more and more researchers have begun to pay attention to the research of online fountain codes. At present, the research on online fountain codes mainly focuses on the following points. 1. The full recovery performance, and 2. Intermediate performance. 3. Unique error protection property. 4. Unique recovery time property. With the research on online fountain codes, they have been applied to many applications such as wireless sense networks and satellite broadcast system. However, the existing methods are designed for unlimited feedback. In practical applications, due to the shortage of feedback resources, the feedback times are usually limited. Therefore, it's a meaningful research direction to study how to efficiently transmit data with online fountain code under limited feedback scenario. My paper focused on the efficient transmission of data in limited feedback scenario. Then, we briefly review the online fountain code and the online fountain code with limited feedback. For the online fountain code, the uniparted graphs are introduced to represent the decoding state, as shown in this figure. An example of the bipartite and the corresponding unipartite graph is presented. The original symbols, or called source symbols, are represented by circle nodes, while the output symbols, or called encoded symbols, are represented by score nodes. In the bipartite graph, if a score nodes are labeled with two circle nodes by edges, it means the corresponding encoded symbol are generated by the XOR of these two source symbols, while in the uniparted graph, the nodes are only used to represent the source symbol. The edge between two nodes indicates that an encoded symbol generated by the XOR of the two source symbols is received by the decoder. Black the node represents the source symbols that have been recovered. I want to introduce the definition of useful symbol. Under the decoder, an accorded symbol is useful when it belongs to the following two cases. Case 1. A received symbol that degree M is the XOR of a single white symbol and M-1 black symbols. Case 2. A received symbol that degree M is the XOR of two white symbols and M-2 black symbols. When the optimum degree value changes, the decoder feeds back the decoding state to the transmitter. Then the transmitter modifies the degree value to transmit encoded symbols. We assume that there are k source symbols. The encoding process of online fountain code is divided into two phases, build-up phase and completion phase. I will first introduce the build-up phase. Build-up phase. The phase consists of two steps. In the first step, the transmitter generates coded symbol with degree 2 continuously. The decoder receives the coded symbols and updates the uniparted graph until the set of the largest component is k beta 0, where beta 0 is a predefined value that satisfies this. The decoder sends feedbacks to inform the transmitter. Then the first step ends at this time. In the second step, the transmitter sends the coded symbol with degree 1 until the largest component is colored black, which means all the source symbols in the largest component is recovered. Then the build-up phase ends. In the completion phase, the transmitter generates degree M coded symbols based on beta until the decoding process is successful. Beta represents the recovery ratio of source symbols. The encoder selects an optimum value of M to maximize the probability of the coded symbol becoming a useful symbol. In other words, to maximize the sum of probabilities of case 1 and 2, then the value of M satisfies the following equations. The above is an introduction of online fountain code with unlimited feedback. In this slide, I will introduce the online fountain code with limited feedback. For the online fountain code with limited feedback, the authors proposed two strategies to select optimum feedback points in all the feedback points. When the number of feedback times is determined, the heuristic table lookup algorithm based on effective probability and the heuristic table lookup algorithm based on overhead are applied to selectively appropriate feedback points to reduce the overhead. But this is some shortcoming, such as since a fixed value of degree is selected between two feedback points, when the number of feedback times is small, the optimum degree value skipped between the two feedback points is too much, so the effective probability of the fixed value of degree M will gradually decrease. This will lead to a high overhead. And the third part, I I will introduce the proposed growth degree encoding scheme for online fountain codes with limited feedback. In the conventional schemes, the degree value of the coded symbol sent by the conventional scheme is from the feedback, which is fixed until the next feedback. However, in our proposed scheme, the degree value between two feedback points is gradually growing. In the proposed JDS scheme, the transmitter gets the selected feedback points from the set of degree transition points according to the HTLEP or HTLO algorithm. We denote by B and M the set of selected feedback points and the corresponding feedback degrees, respectively. When the number of feedback times is determined to be n, we can get the following equations, where beta I and mi represent the S feedback point and the feedback degree. M0 represents the corresponding optimum degree when beta is beta 0. M maximum represents the maximum degree in the scheme. The transmitter sends coded symbols between every two adjacent feedback points. Some transition points will be skipped between any two adjacent feedback points, and the optimum degree value will change at these transition points. We assume the transmitter receives the feedback and knows the decoded symbol ratio beta is beta I between the feedback points beta I加1 plus 1. The skipped transition points are denoted by beta I1, beta I2, beta Ij, and the corresponding transition degree are denoted by mi1, mi2, mij. By combining the set of feedback points and the transition points, we can get the following two sets, where beta I0 and mi0 are the beta I and mi in the set of B and M, respectively. With these two sets, we can derive the set N is the set of coded symbols that needs to be sent between the two feedback points. The dimension of Ni is J plus 1. We denote by Nix the X element in this set. Then Nix can be get by the following equation. The value of Nix represents the theoretical upper band of the number of coded symbols with degree mix when the value of beta is between the transition points bix and bix plus 1. And the fourth part, I will give the theoretical analysis of the online fountain code with limited feedback and the proposed JDS scheme. The analysis is given at the corollary 1 and 2. I will not introduce too much here. And the fifth part, we first verify the proposed analysis by comparing with the simulation results. We assume the k equals 1000 and the beta 0 equals 0.5. We compare the performance for the three feedback points selection strategy, HTLEP, HTLO, and EVM. The EVM strategy is a simple feedback point selection strategy that equals the number of degrees skipped between every two feedback points. This figure shows the overhead performance of the online fountain code with limited feedback and the proposed JDS scheme. For the feedback points selection strategies, we perform analysis and simulations over the lossless channels when the number of feedback time is 1 to 5 as shown in Figure 2. The theoretical analysis matches with the simulation results, which demonstrate the accuracy of our proposed analysis. When the channel is lossless channels, we also observe that compared with the conventional encoding scheme, the GDS scheme can effectively reduce the overhead, especially when the number of feedback time is extremely small. In Table 1 and 2, we compare the overhead performance of conventional scheme and the GDS scheme over the lossy channel. We set the channel erasure Xc equals 0.1 and Xc equals 0.2, as can be seen from the tables. The proposed GDS scheme still has good overhead performance over loss channel, even with the simple even feedback selection strategy. Online fountain codes with limited feedback can achieve very low overhead by using the GDS scheme. In this slide, I give the conclusion. We proposed a gross degree encoding scheme for online fountain codes with limited feedback to achieve a low overhead. Between the two feedback points, the transmitter initially sends a fixed number of coded symbols with gross degree values. When all the coded symbols are transmitted, if no feedback is received at this time, the coded symbols are generated according to the calculated degree distribution until the feedback information is received. We also analyzed the overhead performance of the conventional OS online fountain code with limited feedback and the proposed scheme. Both the theoretical analysis and the simulation results show that the proposed scheme can achieve a significant overhead reduction when the number of feedback time is small. Finally, the above is all the content of my presentation. Thank you for listening.